speed control has been around longer than most people realize. What was once touted as a high-end option is now considered a necessity by many of today's car buyers. In this month's program, we'll be talking about the speed control systems found on Chrysler passenger cars, starting with a look at the evolution of Chrysler speed control systems, how they've changed over the years. Then we'll cover the latest enhancement to speed control, the Interactive Speed Control System, or ISC for short. We'll look at the ISC system's operation and explain some features that make it more responsive to changes in terrain and vehicle load. Of course, we'll also go through some speed control diagnosis and service procedures. And finally, we'll call your attention to some current speed control related issues that you should be aware of. You're probably used to seeing cars with speed control, and you may even have some experience fixing problems with the speed control systems. But did you know that speed control can be found on Chrysler vehicles as far back as the late 1950s? The components have changed over the years, but Chrysler vehicles with speed control still provide the driver the convenience of assisted vehicle control in cruise situations. The family of speed control systems can be classified into three basic generations: electromechanically controlled speed control, PCM-controlled speed control, and today's newest innovation, interactive speed control. These systems are similar in that vacuum is used to adjust the throttle opening to maintain the set speed. The difference lies in the way these systems are controlled. Let's take a look at each type of system to illustrate how speed control has evolved. We'll start with electromechanically controlled speed control, which has been used since the early 70s. This system consisted of a speed control servo assembly, a servo throttle cable, a multifunction control lever, and cables to the transmission and speedometer. There are also stop lamp and clutch switches that complete the speed control circuit when the clutch and brake pedals are not depressed. These components are from a 1982 domestic passenger car. When the servo is electrically activated by the control lever, it mechanically actuates the throttle cable using engine vacuum. The same era's import car speed control system utilized a valve body, a speed sensor that is located in the speedometer head, a dash-mounted speed control switch, and a vacuum motor connected to the throttle lever by a chain. This system used an electronic control module, or ECM, for control. The ECM monitors the vehicle speed through the speed sensor and senses input from the speed control switch. The valve body regulates vacuum supply to the vacuum motor, which controls the throttle lever to achieve the desired vehicle speed. MasterTech has been there every step of the way in the evolution of speed control. We covered speed control service way back in May of 1982. With the advent of electronic control modules around model year 1987, control of the speed control system was delegated to the powertrain control module, or PCM. These second-generation speed control systems were still vacuum operated, but the PCM handled the control on Chrysler domestic vehicles. Other components include the speed control switches, the servo unit and throttle cable, a vacuum reservoir, and stop lamp and park neutral switches. The PCM uses its vehicle speed sensor input and inputs from the speed control switches to determine the desired cruise speed. It then sends outputs to solenoids located in the servo that adjust the amount of vacuum and actuate the throttle cable. Of course, some components and their locations may vary from vehicle to vehicle, but the operation is basically the same for PCM-controlled speed control systems on Chrysler domestic vehicles. This was the subject of the August 1993 MasterTech, titled Speed Control Systems. That brings us to the latest speed control system found on Chrysler passenger cars, interactive speed control. Interactive speed control components include speed control switches, a speed control servo, a vacuum reservoir, and stop lamp switch. This system is termed interactive because there is communication taking place between the powertrain control module, or PCM, and the transmission control module, or TCM. These two modules work together to maintain tighter overall speed control, especially under increased powertrain loading conditions. ISC is found only on vehicles that are equipped with a 41TE or 42LE transaxles, but not all vehicles equipped with these transaxles feature ISC. The major advantage that ISC has over other speed control systems is that it eliminates unnecessary shifting, avoiding the shift busyness that is common under heavy loading conditions with speed control engaged. This provides smoother and quieter operation, which enhances the overall ride of the vehicle and increases customer satisfaction. Interactive speed control also improves required shifts by sensing vehicle loading conditions and scheduling gear shifts accordingly. This produces smoother upshifts and downshifts over hilly terrain or other conditions that affect the load on the vehicle. The ISC system is obviously electronically controlled, but it is vacuum operated, so you can see how it has evolved from the systems we discussed earlier. A list of the vehicles that are equipped with ISC can be found in this month's reference book. Remember, only some vehicles with the 41TE or 42LE transaxles have interactive speed control. In fact, the listed 1993 and 1994 vehicles have ISC only if the TCM has been reflashed or replaced. The reflash procedure was covered in the February 1995 MasterTech on 41TE and 42LE advanced diagnostics. Before we get into the operation of interactive speed control, give this review question a try. What do the three generations of speed control on Chrysler vehicles have in common? A. They all use steering wheel mounted switches. B. All are electronically controlled. Or C. All are vacuum operated. The correct answer is C. All Chrysler speed control systems are operated using engine vacuum. Now that you've seen how interactive speed control has evolved from past systems, let's go over ISC operation. To the driver, operation of ISC is pretty much the same as before. In fact, the enhancements that make up ISC are, for the most part, transparent to the driver. The ISC system uses speed control switch modules with 4 or 5 switches, depending on the vehicle. The switch modules cannot be repaired if found to be faulty. You must replace the entire module. The modes that are controlled by these switches are on-off, cancel, resume accelerate, and set coast. The switch module sends outputs over a single circuit to the PCM when any of the buttons are pressed. Resistive multiplexing in the switch module tells the PCM which switch was pressed. The input voltage from the switch module is measured by the PCM. Since the voltages are different for each mode, the PCM can tell which button the driver pressed. In order for the ISC to become active, the PCM must first see the on button pressed. The PCM will not engage the speed control if it sees the stop lamp switch closed, or if the gear selector is in park or neutral. If those conditions are not present, the PCM will then allow the set speed to be stored in the memory. To store a set speed, the driver depresses the Set Coast switch at the desired speed. The set speed must be between 30 and 85 miles per hour to be stored by the PCM. The PCM determines the set speed through the transaxle output speed sensor signal. Then the PCM controls the amount of vacuum applied to the servo diaphragm, which actuates the servo cable to adjust the throttle opening. The PCM monitors vehicle speed and other inputs while speed control is engaged and makes adjustments to maintain the set speed. If the off button is pressed while the ISC is engaged, the PCM will disengage the speed control and erase the stored set speed. Now let's look at the acceleration and coast features of interactive speed control. Interactive speed control provides an accelerate function to increase the speed of the vehicle while the speed control is engaged. With speed control already engaged, the driver presses and holds the Resume Excel button. The PCM reacts to this switch input by adjusting the vacuum applied to the servo, which increases the throttle opening. The vehicle slowly accelerates as long as the Resume Excel switch is held closed. When the driver releases the Resume Excel switch, the vehicle stops accelerating, and the new set speed is stored in the PCM's memory. Interactive speed control also has a tap-up acceleration feature, used to increase the set speed in steps. This is accomplished when the driver momentarily presses and releases the Resume Excel switch. The PCM increases the set speed 2 miles per hour each time the Resume Excel switch is momentarily pressed. For MMC vehicles, the tap-up feature increases the set speed in 1 mile per hour increments. The ISC system also features a deceleration or coast mode. When the PCM receives the input from the set coast switch, it adjusts the vacuum applied to the servo to decrease the throttle opening, causing the vehicle to decelerate. When the driver releases the set coast switch, the PCM stores the new set speed in its memory and continues speed control operation. Now let's take a look at the ways interactive speed control can be disengaged, both manually and automatically. The driver can manually disengage speed control in 4 ways. If the driver presses the off switch while the speed control is active, the PCM will disengage the speed control and erase the set speed from its memory. If the driver presses the cancel switch while the speed control is active, the PCM will disengage the speed control, but it will keep the set speed stored in its memory. If the driver steps on the brake while the speed control is engaged, this actuates the stop lamp switch, which opens the speed control circuit and disengages the system. The set speed is not erased, however. Likewise, placing the gear selector in park or neutral will disengage speed control, but keep the set speed stored. The PCM senses this through the park neutral switch. Pressing the resume switch will restore speed control at the set speed that was originally recorded with the 3 previous disengagement conditions. Turning the key off will not only disengage speed control, but it will also erase the set speed from the PCM's memory. There are other conditions that will automatically disengage speed control operation, most of which are for safety considerations or to avoid damage to the vehicle. If the PCM sees the vehicle speed signal increasing at more than 10 miles per hour per second, indicating extremely poor traction, it will disengage the ISC. The PCM will also disengage speed control if it sees the vehicle speed signal decreasing at more than 10 miles per hour per second. This indicates rapid vehicle deceleration. Speed control will also be disengaged if the PCM sees excessive engine RPM, indicating that the transmission may be in low gear. Finally, the speed control will be deactivated if the actual vehicle speed is 20 miles per hour or more above the set speed. This changed in model year 1996 from 10 miles per hour or more above the set speed. After any automatic disengagement of speed control, its operation can be restored by pressing the resume switch. This will return the vehicle to the original set speed. You need to know that there are differences in the speed control systems from vehicle to vehicle. This is especially true of Diamond Star and MMC vehicles, like the Sebring, Avenger, and Talon. First off, Chrysler MMC vehicles use what's known as fuzzy logic for transmission shift control. Fuzzy logic is a recently developed technology that's able to express variables in vague terms, such as large and small, or slow and fast, which matches our human perceptions more closely. Conventional control systems require a certain amount of driver input in response to changes in such areas as road conditions and terrain. Fuzzy logic increases the amount of vehicle control supplied by the control module. It senses vehicle and road conditions and makes decisions accordingly. There are also differences in the hardware used on MMC vehicles. Their speed control systems do not use momentary contact switches. The PCM's role in speed control differs too. It doesn't provide power to the on-off circuit, and its internal diagnostics are different from domestic vehicles. And as mentioned earlier, the tap-up acceleration feature uses 1 mile per hour increments. Chrysler import vehicles also have a tap-down feature for speed control that uses 1 mile per hour increments. And finally, the minimum set speed for import vehicles is 25 miles per hour, as opposed to 30 miles per hour for domestic vehicles. Before we get into the real interactive side of interactive speed control, try answering another review question. With speed control engaged, which of these actions will not erase the set speed from the PCM's memory? A. Pressing the cancel switch. B. Pressing the off switch. Or C. Turning the key off. The correct answer is A. Pressing the cancel switch will disengage speed control, but the set speed will remain stored in the PCM's memory. Up to now, you may think that interactive speed control is not all that different from previous speed control systems. As we told you earlier, many of the features of ISC may go unnoticed by the driver. But let's look at what makes the system truly interactive. You'll find a discussion of interactive speed control in Technical Service Bulletin number 8-1595, Revision A. Reading this TSB should give you a good start on understanding the differences. We told you earlier that interactive means communication between the PCM and the TCM. Let's talk about the new features of interactive speed control, and then we'll see the system in action. One new feature used with ISC is improved gear selection when the vehicle is under load. Actually, this is a feature of the TCM. Improved gear selection under load always operates, whether ISC is engaged or not. Improved gear selection means that the TCM will inhibit the scheduled upshift based on the load conditions of the powertrain. This feature applies only to upshifts. During ISC operation, to maintain the set speed, the TCM and PCM identify powertrain load values. The load is calculated using MAP, RPM, and throttle angle. Under moderate loads, the TCM will keep the transmission in third gear until the load is reduced, such as reaching the top of a hill. Under severe load, 1996 vehicles with 41 TE or 42 LE transaxles may downshift to second gear and remain there until the load is reduced. The TCM would then schedule a second to third gear upshift and maintain the set speed. Other severe loading conditions can include trailer towing and extreme headwinds. The downshift delay feature of ISC, new for 1996 vehicles, reduces the frequency of downshifts over hilly terrain. It operates only when ISC is engaged. 1995 vehicles do not have the downshift delay feature, so an overdrive to third to second downshift may occur quickly without the vehicle losing significant speed. The TCM delays or avoids a downshift, while the PCM increases the throttle opening to nearly wide open throttle to maintain the set speed. The downshift delay feature will operate as long as the vehicle speed is within 3 miles per hour of the set speed. This feature helps reduce wear on the transaxle. In addition to disengaging the speed control, there are 2 ways the driver can deactivate the downshift delay. If the driver manually overrides the throttle position, the downshift delay will not operate. And manually downshifting will also deactivate downshift delay operation. You may be wondering if ISC or any of its features affect torque converter clutch engagement. Only upshifts and downshifts are affected by ISC, and torque converter clutch engagement is not affected at all. Now let's see the system in action by watching what happens when the vehicle ascends and descends a hill with the ISC engaged. When a vehicle climbs a steep grade with the ISC engaged, the PCM and TCM work together to maintain the set speed. The ISC system first tries to maintain the set speed by increasing the throttle opening. If the set speed is maintained, no downshift is scheduled. However, a torque converter unlock shift may occur. But if the vehicle speed drops more than approximately 3 miles per hour below the set speed, a downshift will occur. If the grade is severe and the vehicle speed continues to decrease, the TCM will schedule a further downshift. It will upshift when the vehicle can maintain the set speed in the next highest gear. Remember, these shifts are heavily dependent on vehicle load. The PCM provides the map value used with the throttle angle and RPM to calculate the load to the TCM, which then makes the shift decisions. Now let's look at what happens when the vehicle comes down the hill. While descending a grade, the ISC system provides for overspeed reduction. When the vehicle first starts down the hill, the ISC tries to maintain the set speed by reducing the throttle opening. The speed control servo will reduce the throttle opening to closed throttle if necessary to maintain the set speed. The throttle is considered closed when the PCM sees TPS at 2 degrees or less. If the vehicle maintains the set speed, no downshift will be scheduled. But if the vehicle speed exceeds the set speed by more than 3 miles per hour and the vehicle continues to accelerate, the TCM will downshift the transmission into third gear, providing engine braking. It will not downshift further. The TCM will shift the transmission back to overdrive when the ISC system sees TPS at greater than approximately 3 to 8 degrees, depending on the vehicle, for longer than 2.5 seconds. While TPS is wired directly to the TCM, the PCM and TCM communicate using bus messages to operate the ISC system. The values that are sent from the PCM to the TCM are speed control on, the set speed, and map. Next, we'll cover some diagnosis and service procedures on the speed control system. But first, give this review question a try. While descending a steep grade, when will the ISC system downshift the transaxle into third gear? A, when the vehicle speed is equal to the set speed. B, when the vehicle speed exceeds the set speed by more than 3 miles per hour. Or C, when the vehicle reaches the bottom of the grade. The correct answer is B. To provide overspeed reduction, the ISC system will downshift the transaxle when the vehicle accelerates to more than 3 miles per hour greater than the set speed. Now we're going to go through diagnosis of the speed control system. This will be a procedure that applies to standard speed control as well, because it's the software of the TCM that determines if the speed control is interactive or not. Of course, to begin any diagnosis, you should check for diagnostic trouble codes with the DRB3 scan tool. This procedure assumes no trouble codes are present. And always be sure to follow the steps in the appropriate diagnostic procedures manual. Test SC1A will address a speed control system that is inoperative. After checking for codes, you should verify the complaint by test driving the vehicle and attempting to duplicate the problem. To begin diagnosis on an inoperative speed control system, connect the DRB3 to the vehicle's data link connector. Then select the speed control monitor so you can verify the operation of the speed control switches. Turn the ignition on, but do not start the vehicle. While watching the DRB3 display, press the speed control on switch. The DRB3 display should show the speed control switch change state. If not, perform the switch test in the Diagnostic Procedures Manual. Check the function of the other switches as well. If any switch fails the function check, repair or replace it as outlined in the manual. Now press and release the brake pedal several times while observing the DRB3 display. This checks the operation of the stop lamp switch. A fault in the stop lamp switch circuit will inhibit speed control operation. If the switch checks out, verify the proper operation of the park neutral switch by placing the gear selector in drive. The DRB3 should show the park neutral switch as drive reverse. As you know, speed control won't operate if the PCM thinks the vehicle is in park or neutral. Now you know all the switches are good, so let's move on to the other components. With the key off, disconnect the speed control servo connector and inspect its condition. If any terminals are bent, pushed out, spread, or miswired, repair is necessary. Also, be sure to check the connector crimp. Once you are satisfied there are no problems with the connector, check the ground circuit with a DRB3 in the ohm meter mode. If necessary, repair the open to ground. After verifying a good ground, test SC1B directs us to turn the ignition on and actuate the speed control vent solenoid with the DRB3. Then probe the speed control power supply circuit with a voltmeter function. If the voltage is less than 10 volts, there could be an open in the speed control power supply circuit. If the voltage is greater than 10 volts, reconnect the speed control servo connector. Then start the vehicle and allow it to idle for 1 minute. After the engine has run for a minute, turn the engine off. Then turn the key on. With the DRB3, actuate the speed control vent and vacuum solenoids while observing the throttle body. A properly functioning servo will move the throttle open and closed. But if the servo fails to operate, this points to either a vacuum leak or a problem with the servo. If the servo operates the throttle, you should use the DRB3 to check for speed control denied messages. This procedure is outlined in the Diagnostic Procedures Manual. Let's assume ours doesn't move and proceed with the diagnosis. Turn the key off. Then disconnect the vacuum supply hose from the speed control servo. Leave the hose connected to the vacuum reservoir. Attach a vacuum gauge to the end of the hose and start the engine. The vacuum gauge should show manifold vacuum. If not, check for a leak or restriction in the vacuum supply line. With the gauge showing manifold vacuum, turn the engine on. Watch the vacuum gauge closely. The system should hold a vacuum for at least 10 seconds. If it doesn't, replace the vacuum reservoir. If you know that the system is holding vacuum, inspect the speed control throttle cable for damage, as described in test SC1C. Repair or replace the cable if necessary. With the key off, disconnect the speed control servo connector and the PCM harness connectors. Use the ohm meter function to check the speed control vacuum solenoid control circuit. If the resistance is more than 5 ohms, repair the open circuit. Perform the same resistance check on the speed control vent solenoid control circuit. Again, there should be continuity, or there is an open in the circuit you should repair. Now that you've ruled out vacuum leaks or electrical problems, the speed control servo has to be the problem. Remove the servo by loosening the nuts attaching the speed control cable and mounting bracket to the servo. Disconnect the connector and vacuum hose. Then pull the cable away from the servo and remove the retaining clip. While installing the new servo, be sure to keep the throttle in the full open position to align the holes in the cable sleeve and the servo pin. Then reinstall the retaining clip. Reconnect the vacuum supply hose and electrical connector and secure the servo to the bracket. Remember to follow the procedures in the Diagnostic Procedures Manual, as components and systems vary from vehicle to vehicle. Now we'd like to mention some technical service bulletins related to speed control. The TSB that discusses interactive speed control operation is number 81595, Revision A. TSB number 182495 covers transaxle shift quality improvements. The repair will result in adding the overspeed reduction feature of ISC to the programming in the TCM on 1993 and 1994 vehicles equipped with the 41TE or 42LE transaxles. And TSB number 81695, Revision A, addresses speed control overshoot and undershoot of the set speed due to excess slack in the speed control servo cable. You should now be more familiar with Chrysler speed control systems, and MasterTech will continue to update you on new features of Chrysler vehicles. That's all for this month's program. We'll see you next month. Occasionally on MasterTech, the diagnosis leads to the need to replace a component or assembly. And that's the reason for this special segment, to talk to you about why Mopar remanufactured parts are a good choice for your replacement parts needs. Now, some of you may substitute the terms rebuilt or even used when you hear the term remanufactured, but that's just not the case, and for several good reasons. And to prove it, we're going to take a look at a couple of remanufactured assemblies and the advantages they can offer you. Our first example is the 8-liter V10 used on Dodge Ram pickups. The Magnum V10 is remanufactured by specialists in the field of engine design, production, and remanufacturing. The result is an engine that is approved by Dodge Truck Engineering for use under the new vehicle powertrain warranty. One reason for the high level of quality built into Mopar remanufactured parts is the close working relationship between Mopar, the remanufacturer, and Dodge Truck Engineering. Here's how Mike Beavers, senior project engineer with the V10 project, describes it.
Been very, very heavily involved since day one on this remanufacturing project. And what that does is when we speak with the Dodge engineers, they tell us of things that are happening, things that are changing, and we let them know what we're doing so they can be assured and Chrysler can be assured that they are getting a consistent quality product.
Here's a look at the V10 reman process from start to finish. The V10 reman process begins when the engines arrive at the plant. These are the cores that dealerships return to Chrysler. As the engines are unpacked, they are visually inspected for any obvious damage or flaws. Next, the engines are disassembled. Most components, even if they haven't failed, will be replaced with new parts. These include the camshaft and related items, timing chain, valve train, water pump, pistons, fuel rail, fuel injectors, and all fasteners, seals, and gaskets. The automatic replacement of key parts is an important difference between a remanufactured engine and a rebuilt one. While many engine components are replaced, major components such as the crankshaft, cylinder block, cylinder heads, and connecting rods are inspected, requalified, and tested using state-of-the-art methods. After engines have been completely disassembled, components are cleaned using a variety of methods ranging from pre-soaks to high-pressure steam cleaning, steam rinsing, and chemical baths. The goal is to remove any soot or debris that might interfere with the machining process. The cleaned components are then processed to help ensure they meet Chrysler original equipment specifications. All critical dimensions of the engine block, for example, are inspected using a variety of techniques, including air gauging, magnaflux, and surface analysis. The main bearing bores are checked and measured for alignment, and the lifter bores are also checked for wear. The cylinder head inspection includes water pressure testing, in which plates are put on the top and bottom of the head to seal the water jackets, and the head is submerged into a tank of water. Then 45 to 50 psi of air is injected into the head. If air bubbles are visible, they indicate a crack in the head. Any damaged heads are scrapped. The crankshaft also undergoes detailed inspection. To check for cracks and wear on the bearing surfaces, for example, the crankshaft is sprayed with a fluorescent penetrant and then isolated in a darkened chamber. By shining an ultraviolet light on the crankshaft, inspectors can identify any cracks or wear indications. The inspection process is only one of the ways in which high-tech techniques have transformed remanufacturing into a process that guarantees quality. The application of high technology to the remanufacturing process continues during machining, when components are brought back to original equipment specifications. Cylinder bores are precisely machined to ensure proper piston ring sealing and oil control. This machining is monitored using statistical process control to help ensure consistent bore finish. After the bores are honed, they are measured using a surface analyzer that acts like a phonograph stylus to map the surface of the bore. A smooth surface on the bore is critical to engine emissions and performance. The surface analyzer equipment generates a computerized image that tells whether the surface is within tolerances. Crankshafts are also precision machined to meet specifications, and all corresponding journals are match machined to the nearest undersized OEM specifications. Then crankshafts are expertly polished to create a smooth, contaminant-free surface. Other procedures performed during the requalification process include the machining of the cylinder head mating surface. The V10 cylinder head provides us with another example of the advantages of remanufactured parts, and that is the ability to incorporate improvements to components into the reman process. With the V10 cylinder head, an engineering change to fuel injectors resulted in 1995 engines having a larger clearance area. To take advantage of these improvements, the remanufacturing process includes machining the cylinder head on pre-1995 units to accommodate the newer injectors. Once again, we'll have Mike Beavers, Senior Project Engineer, explain the close connection between the remanufacturer and Dodge Truck Engineering.
In our reman program, we are in constant contact with folks at Truck Engineering. And through that contact, we learn of new updates to existing products. And what we do is we will take old products and add the new specifications to them. So the customer gets the newest specifications on even their older engines.
In the final stage of assembly, all bolts and fasteners are tightened using computer-controlled torque wrenches that ensure accuracy and consistency. Finally, after the engines have been assembled, they are run in simulation tests to verify performance. Engines passing inspection are fitted with water pumps and fuel rails, and then packaged in special containers for shipment to the regional part depots. Another advantage of the Mopar remanufactured V10 is that it arrives at the dealership as a drop-in assembly. Technicians only need to reinstall wiring harnesses and the thermostat housing. Everything else is included on the engine. Now let's turn our attention to another Mopar remanufactured assembly, the 41TE transaxle. As you may know, Chrysler requires that reman units be used for warranty repairs to 1989 through 1994 vehicles equipped with the 41TE transaxle. Warranty bulletins D9427 and D9513 describe the affected vehicles. As with the V10 engine, improvements have been incorporated into the transaxle reman process. These improvements are aimed at eliminating possible concerns associated with original equipment transaxles. One of the concerns was a bump felt during the 2-1 downshift, sometimes referred to as a coast down bump, since it typically occurs when the vehicle is coasting to a stop. All Mopar remanufactured 41TEs are now subject to a new, tighter specification for clutch pack clearance. This should greatly reduce the coast down bump. Another shift quality concern involved a shudder that occurred at the 1-2 shift. Chrysler has revised the clutch friction material, and this material is now used in all Mopar reman 41TEs. Plus, a change to the 2-4 piston retainer also improved the quality of the 1-2 shift. Reman 41TEs for 1991 and 1992 model years use valve body assemblies capable of providing partial EMCC, or electronically modulated converter clutch operation. In fact, all Reman 41TEs use valve bodies that have been modified to incorporate the latest levels of engineering changes. Low reverse and 2-4 piston seal leaks have been another area of concern. The seals on these pistons occasionally have cuts in them. Chrysler has switched to a new D-type seal design to help eliminate this problem. Seal swelling has also been an area of concern. For this reason, in May of last year, seal material was changed to Viton on several key seals in 41TE input clutch assemblies. Other revisions that the Reman 41TEs have adopted include the switch to a tapered snap ring for the underdrive-overdrive reaction plate and a revised overdrive hub that is stronger. Concerns about output speed sensors have also been addressed. Each sensor is now tested under actual operating conditions. In another change aimed at improving reliability, torque converters now use bonded friction discs. Output and transfer gear teeth angles have been revised. 1989 and 90 41 TEs used 27.5-degree output and transfer gears. All 1991 and later Reman transaxles are built with 32-degree output transfer gears and related components to reduce gear whine. Of course, some 41 TE noises are normal, such as a certain amount of ratcheting type noise from the solenoids. With the quality control procedures built into the Reman process, you can rest assured that components such as solenoids are working properly. Just as with output speed sensors, solenoid packs are tested on the transaxles for proper operation before they leave the factory. In addition, you can keep such noise to a minimum by making sure the solenoid sound shield is properly installed. As we've seen, one advantage of Mopar Reman 41 TEs is that they incorporate improvements that are aimed at providing smooth operation and reliability. As a result, in many cases, a Reman 41 TE may perform better than the original. Another advantage is the rigid quality control. Reman 41 TEs are thoroughly tested before they're shipped. Each one is checked on a dynamometer and with a DRB scan tool. Mopar remanufactured parts are constantly being improved with the latest engineering refinements to provide you with the highest quality replacement parts available. Many of these refinements require you to use updated diagnostic and installation procedures. For the latest information on these updates, don't hesitate to call the STAR hotline at 1-800-850-7827 or the appropriate product hotline from the list on page 6 in the Mopar Remanufactured Parts catalog. Hotline technical specialists are interested in helping you do the job right the first time and getting your feedback on Mopar Remanufactured products, too. Thanks for joining us for this look at Mopar Remanufactured Parts. When you think about it, using Reman parts makes sense, both from the customer's point of view in terms of price and from your point of view in terms of reliability.